All right, welcome back. 13.3, working in thermochemistry. Again, that's chemistry that deals with energy or heat, thermo. Today, we're looking at energy or enthalpy that is associated with the changes in temperature. We actually worked with this already a little bit in a lab last chapter. So yesterday, we looked at the enthalpy of fusion or vaporization, which again is the delta H fused, delta H vape, or the other way of writing it, the delta H solid and delta H cond, depending on which direction you're going. And these were the amounts of energy, enthalpy, that is associated with a phase change, how much energy to melt ice, how much energy to vaporize water. Well, today, we're going to look at the amount of energy to change the temperature of a substance. It'll usually be water, or oftentimes it'll be water that we're working with, but not always. So, if you think about it, we have a cube of ice. We melt that cube of ice. We would now have water at 0 degrees. It's not going to vaporize. Water must first be brought up to the boiling point of water, which is 100 degrees Celsius. In order to do that, there's a different formula. We must add energy, and there's a different formula associated with the amount of energy to bring up the temperature of a substance. Again, you've seen this formula before. We used it to calculate the amount of energy in a reaction when we dissolved the magnesium ribbon in the hydrochloric acid. Q stands for energy. We usually measure it in joules, although it could be measured in kilojoules as well. M stands for the mass, which is measured in grams. C is a specific heat, which has the unit of joules per gram degree Celsius. And finally, delta T, delta from math class, is a change of. T is temperature, so the change in temperature. Make sure you're always doing your final temperature minus your initial temperature. The positives and negatives in this chapter will be very important. And we want to make sure that we have a negative amount of energy when we need a negative amount of energy. The way to do that is make sure you're subtracting your final minus your initial. So C, a little bit more about C, specific heat. Every substance has its own unique C, specific heat. Here is a chart, a list of several of them. And for your homeworks, you'll want to refer back to this chart to reference your C's, your specific heats. On a test, you'd be given the tables, so I'd give you the specific heats you need, but again, for your homeworks, you'll just have to reference this particular slide to find the heat capacity, or the specific heat. So, the idea is, go back here a little bit, ever jumped into a pool on a hot day that's early in the spring? Water has a very high specific heat, 4.184. That's incredibly high. Now it's listed here as 4.186, but that's because this is at 25 degrees Celsius, and we're usually going to be working with it at 0 degrees Celsius. So 4.184. That's a very high specific heat. What does that mean? Well, it means that it's going to take a lot of energy. So per gram of material, it's going to take 4.184 joules of energy to raise that substance by 1 degree Celsius. Again, that's a really large specific heat. So even though the air might be really hot on a nice warm spring day, the water in that pool or the water in that lake is going to take a lot longer to warm up. More energy is going to have to shine in that pool. That water is going to need to absorb more energy. Again, look at air. Specific heat of only 1.02, so that air is going to heat up 4 times faster than the water. Another example, you ever sat on metal bleachers on a cool evening after a warm day? So if you go to a football game or any sporting event, and you take a seat on those metal bleachers, and even though the day was incredibly warm, really nice, hot, warm day, those metal bleachers are going to feel cold to the touch. They lose heat very, very fast. Most metals, you look over here, most of the metals have a very small specific heat, less than 1. Which again, that means that it doesn't take much energy to warm them up, or that they lose energy very, very, very quickly. Aluminum bleachers, 0.9, that's actually a fairly large specific heat for metal, but aluminum bleachers are going to lose heat almost 5 times faster than water will. Or for that matter, they gain heat. It would only take 0.9 joules of energy per gram of aluminum to raise it by 1 degree Celsius. So this variable, C, which stands for specific heat, is a constant, and it's unique to every single substance on Earth. Each substance has its own. Ice has a specific heat, steam has a specific heat, vegetable oil has a specific heat. They're all different from one another. They're all unique. Again, you'll be given a table on the test. You don't need to memorize anything, but here is one for your homework. Work through some examples with you here. So the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the copper absorbs 849 joules of heat. And they're asking, what is the specific heat of copper? Ladies and gentlemen, I really like to list out my variables. I think it really helps to see what I have. My formula is Q is equal to M times C times delta T. I was given an energy, Q, 849 joules, there that is. So list that out. I was given a mass, 95.4 grams of copper. They are asking for the specific heat, so that's what we're trying to solve for. And they gave us a final temperature from 25 to 48, so we're going to 48, that's our final temperature. And our initial temperature was 25 degrees Celsius. So our delta T, our change in temperature, will be 48 minus 25 is 23 degrees Celsius. I'm trying to solve for C, so I want to isolate that variable. If I divide both sides by the mass and the delta T, I'll have C on a side by itself. Now I can plug in my variables, 849 joules divided by 95.4 grams times 23 degrees Celsius. Don't forget your units in your work. And now we see why a specific heat has a unit of joules per gram degree Celsius. Try another example. How much heat is required to raise the temperature of 250 grams of mercury by 52 degrees Celsius? Again, we might need to reference the specific heat of mercury from the table 2 slides ago, but I'm going to start by listing out my variables. The formula I'm looking for is Q is equal to M times C times delta T, and they're asking how much heat. Heat is energy, so that's our Q. They gave us a mass of 250 grams. Our specific heat, 0.140, and again, if you're forgetting where we got that from, we're looking for mercury, there it is, specific heat of 0.140 joules per gram degree Celsius. Our change in temperature is 52 degrees Celsius. Kind of a hint, oftentimes if they don't give you 2 degrees Celsius, they're giving you the change. So we're changing it by 52 degrees Celsius. That's the entire change. Again, I'm looking for Q. I've already got my variable isolated. The Q is isolated already. So now I just need to plug in my variables. Don't forget to show your units in your work. Crunch the numbers in your calculator. It should end up with 1,820 joules of energy is going to be required to heat a 250 gram piece of mercury by 52 degrees Celsius. All right, homework number 3 for this unit. Again, working with some different masses, some different energies, some different changes of temperature. Take a look. See how you do. Good luck.